welcome everybody. So just to give you a little bit of an outline, we're not expecting this to be a very long session, about half an hour or so. So I'm going to spend the first few minutes just setting the scenes in terms of what Maplesoft's engineering solutions group is about, and the technologies we're going to be talking about specifically in this session. I'm then going to hand over to John McPhee, John McPhee at the University of Waterloo, who's going to go through some of the motivating factors that have driven them to come to this sort of workflow for taking data or model data from Adam's car to implement it within MapleSim, specifically for entering in or to adding further detail to the vehicle model for electric vehicle drives. We then go to Andrew Hall, who will go through the workflow that they've been working on to develop an equivalent chassis model within MapleSim that will effectively create the same type of model, the same chassis model within MapleSim from the data from the Adams car model. A lot of this, this particular seminar has been driven by really Maplesoft wondering about whether this actually would make a viable product. So really part of this session is us asking you, those of you who are interested in doing this kind of thing, just the level of interest you would have in having a product that would allow you to do this automatically. So at the moment it's still a bit of a manual process, as you'll see in the session, but we do see how we could actually turn this into a product that could automate the whole process. So at the end I'll go through a proposal on that. I want to wrap this up with the session at the end with a survey, so you'll be pointed to an online survey where you can answer just a few simple questions, just to give us a sense of what your level of interest would be in such a tool. So let me just start by giving an introduction to the Engineering Solutions Group. We provide a combination of engineering tools for doing advanced analysis, and really to help our clients to solve challenging engineering problems. So this includes Maple, which we've had for many years as a tool for doing parametric analysis and optimizations from physics-based models were developed inside of MapleSim. The core, or at the core of all this, is the fact that we're using our symbolic technology to represent the system models at an equation level, which actually makes it very concise and very suitable for doing code generation. And in fact, we can make the claim that because of using this approach, we can produce the fastest possible automatically generated code from those models. The only way you're going to be able to do this faster would be to write the code yourself. We combine that with essentially my group, which is the professional services group. So if you need to be able to do this kind of work, we can advise you on how the best approach to do it. We can even help you actually into doing it yourself, or do it completely for you. So that's really what the whole Engineering Solutions Group is about. The kinds of functions that we carry out have been largely in the product design side, so design validation and optimization, effectively creating virtual prototypes of your system so you can get a better sense of where the design issues are likely to be before you start investing in the prototyping stages. The area we want to focus on today is really just this whole notion of physics-based system-level simulations. So the idea of being able to take multiple subsystems and combine them together into one environment in order to gain understanding on how the various different subsystems will interact with each other. And this is critically important. You can make what seems to be a very innocent change in one subsystem, and this can have a very detrimental effect on other subsystems within. And it's only when you start visualizing or the complete system with all the various subsystems interacting with each other that you are able to identify what those issues are. What the other aspect that we'll talk about in this particular session is the fact that once you've done all this, you can then generate optimized code for hardware in the loop, software in the loop, component in the loop kinds of testing. So let me talk just a little bit specifically about MapleSim, in case you're not aware of MapleSim as a product. So MapleSim is a tool that allows you to do this system-level simulation by combining subsystems that can have many different domains. So you can have electrical, mechanical, magnetic, hydraulics, gas flow, thermal, all within one environment. So you can get a very clear sense of how the whole systems or set of subsystems are going to interact with each other. We use a very easy-to-use schematic level or schematic diagram type of user interface for allowing you to rapidly develop these models. It's an acausal representation that's been driven by various movements, but we are deeply involved in the Modelica association, and this is where much of the acausal representation has been driven. So essentially, it's a much easier way of being able to get models to work, or plant models to work inside a simulation without having to go through the sequence of generating mathematical equations and then using the tools like Simulink to develop signal flow models. I'm getting a note here that I'm very quiet. I'll just bring the microphone a little bit closer. This is all based on the Maple symbolic foundation. So as I mentioned before, by using the symbolic approach to formulating the models, we come up with very concise representations that are numerically efficient and can be then used for doing code generation and very fast simulations for optimizations and so forth. Also, we should be very clear that it leverages the power of Maple for doing analyses from those models. So things like sensitivity analysis, optimizations, parameter studies can all be done with Maple that is fully integrated with the MapleSim environment. And we've heard from many of our clients that by using this approach for doing the physical modeling of our systems, that reduces the model development time very significantly. Sometimes what used to take months can be done in a matter of days in order to produce these high fidelity and high performance models. So as a sort of a lead into Dr. McPhee's part of the presentation, one of the areas that we've been very active is in the study of electric vehicles and hybrid electric vehicles. And again, this whole notion of being able to combine multiple systems onto a vehicle chassis in order to understand how the various subsystems will interact with each other. And this includes batteries and the engine and the electric drives. Coupling all these domains together can obviously produce unexpected responses if you make any changes. So really what we're going to be showing here is how we can extract the chassis information or the chassis model information from the Adams car environment into the MapleSim environment to do this kind of study. So with that, I'll pass the microphone over to Dr. McPhee to take you through the motivating factors behind this project.
Okay, thanks very much, Paul. So I guess I'm going to fill in the blanks between Paul's opening and Andrew's very detailed presentation about modeling chassis within MapleSim, starting with an Adams car model. I'm an industrial research chair supported by Toyota and Maplesoft, and I'll just start by giving a little bit of background about our chair objectives. In particular, working with Toyota engineers, we're trying to develop math-based models that allow us to look under the hood, if you pardon the pun, to see the physics and the chemistry behind how individual components perform and then how they are integrated together to create a system-level model. And because we are very keen to see those underlying equations, to understand the physics and the chemistry, we've chosen Maple and MapleSim as our supporting tool for this project. It's actually a 5-year research program. Maple gives us more than just access to the equations. It gives us powerful utilities to manipulate those equations. Now, Paul's already talked about automatically generating sensitivity analysis, which is something that we have done for electric and hybrid electric vehicle models. We've used those to develop optimized designs as well as optimized controllers and identify unknown model parameters for our systems, such as electric vehicles and hybrid electric vehicles. Now, one thing that people don't think about when they think of Maple is generation of very fast simulation code. I don't think people think about that when they think about the Maple symbolic computing platform. But really, in my opinion, that's the strength of symbolic computing. We can do very deep model reduction and simplification, generate highly optimized simulation code, and that allows us to do control systems development and testing and hardware in the loop. And in this particular picture, this is one of the benches in my lab where we have a simple driving interface. We have a quad-core real-time computer from National Instruments. On one of those 4 processors is a MapleSim model of an electric vehicle with in-wheel hub motors. Connected to it is a Mototron controller, which is connected through a CAN bus, on which we are testing a vehicle dynamics controller for this particular vehicle. Now, what I want to focus on next is some controllers we've been developing very recently on managing the flow of power within electric vehicles and hybrid electric vehicles. So what we've done then is we've gone back into our quad-core processor and we've replaced the previous electric vehicle model with a series HEV model, again developed in MapleSim, I'll show it to you in a second, and exported as highly optimized simulation code. We have the Mototron controller again, our ECU, but this time we've implemented a real-time optimal controller that's based on Pontryagin's minimum principle developed by Reza Razavian. And what this controller does is it manages the flow of power in the system to minimize fuel consumption. So we can go farther on the same tank of gas. We could simulate the battery within this environment, or what we've done in this particular setup is we have a real-time battery cycler with a real cell mounted in it, which is involved in a component-in-the-loop simulation. We chose to do that, but we could easily have simulated the battery within this environment, again in real time, using the power of MapleSim. And what we found is we've got very good agreement between our battery experiments and the battery models that have been developed by Dow et al. Within the MapleSim environment. So let's have a look at that series HEV. This is a schematic of the vehicle. It uses a nickel metal hydride battery pack. It has a mean value internal combustion engine model that we developed in my lab. The vehicle has a mass of about 1,400 kilos. Now, we could simply have a simple one-dimensional longitudinal model for this vehicle, but vehicles do corner and turn and change directions, and so on top of the powertrain and the tires, which have rolling resistance, we have a complete vehicle dynamics model. In this case, a 14-degree of freedom model. 6 degrees of freedom for the chassis, a degree of freedom for each of the suspensions, and wheel spin for each of the 4 tires. The tires themselves have been modeled using the Pacheco 2002 model. Here's a little snapshot of the series hybrid powertrain. We have 2 motors, or 1 motor through a drivetrain driving the wheels. They get their power from a battery. When the state of charge of the battery gets too low, the internal combustion engine turns on, drives the generator to recharge the battery. Our schematic model in MapleSim looks like this. Up in the left here, we can see the engine, including a throttle, a intake manifold, engine where the combustion takes place, and we have a sensor here to measure our fuel consumption. That will drive a motor generator to recharge the battery, shown here in orange. which in turn provides power to our traction motors, which drives the vehicle dynamics model down in the lower right. And it's this vehicle dynamics model that really has taken quite a bit of development time. And this is why we've developed some new tools for rapidly developing chassis model, similar to the sort of modeling framework you see within Adam's car. So here's a very simple schematic that Andrew's going to explain in a bit more detail shortly. So here's our vehicle chassis. Here are our 4 tires, 2 on each side, and the DW are blocks representing an entire double wishbone suspension. These are basically plug-and-play suspension components, and we could replace this with a McPherson or a trailing arm or a multi-link, and it's simply connecting the lines in order to change one suspension with another. The ST means that we have steering, and that's what the green lines represent as steering signals to the front tires. So just a little bit more on that model simplification and reduction. Before we do the equation simplification, over 600 differential algebraic equations to solve. Afterwards, we have only 40 differential algebraic equations, which are easily solved in real time in our hardware-in-the-loop simulation, including all of the physics for the engine, the battery, the motor generators, and the vehicle dynamics that Andrew will talk about now.
Hi everyone, hopefully you can see my screen. So I'm going to talk about the specifics of converting the chassis model in Adam's car to a MapleSim chassis model. So there's 2 different categories of information that are required to do this. The first is the topology of the system, so what it looks like from the outside, the type of suspension, how the chassis is modeled. And then the second is the parameter values, so those are the hardpoint locations and the component masses. We've used the Adam's car shared, the standard demo model that comes with Adam's car as the basis for this demo, just so that everyone can reproduce the work if they want to. And so this is the 3D rendering of the MapleSim model that's generated. So the system topology, the most important part is the suspension. And at the moment, we have 3 different suspension topologies that can be represented: double wishbone, McPherson, and multi-link. And as Professor McPhee mentioned, they can be steered or fixed, and also kinematic or compliant. So if they're compliant, we use bushings to represent the joints between the linkages. And if it's kinematic, then we use standard multibody constraints, like revolute joints, for example. So the other components in the model are, or the other major components in the model are the chassis and the tires. The chassis can be modeled either as a simple rigid body or as a flexible chassis. And there's numerous tires defined in the MapleSim tire library, which is already included. And at the moment we're using Pajeka, but you can also use a linear tire model, a Fiala tire model, or define your own custom tire model. So here's the overview of the model, of the chassis model, as it's defined in the MapleSim user interface. In the middle, we have the chassis, and the input to this subsystem is the steering input. And then at each of the 4 corners, we have a double wishbone suspension. As was mentioned, the front is steered, which is why we have the additional green link. And the black dot means that in this example, we're using a compliant suspension. And then on the outside, we have the four wheels. So how you would go about constructing this system is you'd start with the chassis component, and then dragging in from the library, you would add a double wishbone and a tire to represent the front left suspension. Next, you would do the rear left suspension, and then duplicate this onto the right side. And once you join everything up, you have a complete chassis model. So it's really quite quick to get your model topology defined and ready for the simulation. And then the second stage of the process is to enter your parameters. At the moment, we're doing this manually, but it's going to be automated in the future, and so this will pull directly the model parameters from an Adams car model. And we start with the hardpoint locations, the rigid body mass properties, any bushing stiffness and damping, and also the spring and damper properties. And just an example here, you have the XYZ of a particular hardpoint and the rigid body mass properties of the lower control arm. So I have a short example prepared just to show the workflow. So here we start with the chassis model, which has already been dragged in, and then I've actually cheated a bit and predefined everything. So we drag in the front left and connect that, and then do the same for the rear left, and then adding the tires is simply dragging this block in, and then that's the left side of the vehicle defined in terms of the topology. And then to do the right side is a simple case of repeating that process. To enter the parameters, we have all the data entry on the right side of the screen here, and the tire model we have here is, in this example, is the Fiala. And yeah, and so when we can then drag in a sine wave as the steering input, just for a really basic example. And after simulating, I've removed the CAD image of the body just so you can see the suspension. And once the simulations run, you can see the 3D animation of the model in action. So going back to the slides, just like John already showed the hybrid electric vehicles and electric vehicles as one example of a multi-domain model, but a second application is being done by a colleague of mine in our lab, Nasser Marabi, and he's modeling electronic power steering. And in this case, we also need multi-domain modeling, and he's using the suspension library, as you can see from the CAD image. So in the electrical domain, he models the electric motor and then uses that in his EPS model. And here's an animation of his model in action. And he has a biomechanical model, an 11 musculoskeletal model representing the driver, and the EPS model and the full vehicle dynamics model. And the graph on the right here, you can see the impact of his EPS controller on the steering maneuver. The steering torque for the driver is greatly reduced with the EPS turned on. And these are the references for some of this work if you're interested to learn more about it. And I'll pass it back to Paul, I think.
Yeah. Thanks very much, Andrew. So I'm just going to wrap up. So really, what you've seen with the work that John and Andrew have been doing here is, it's a manual process, but they've certainly found a huge amount of value in being able to take the data in terms of the topology and the configuration data parameters from Adams Car and bring them into MapleSim. Clearly, with Adams Car, it's a major challenge to be able to add further multi-domain subsystems into that environment, and we've heard it many times that it is cumbersome and expensive to do that. And really, the only option you have is to use co-simulation, which is computationally expensive, and then ties up an Adams license where you may not actually need to do anything more with the in the Adams environment. Clearly, because of the computational model that Adams Car uses, it's not possible to implement Adams Car models in real-time applications. So you're left with the option to be able to transfer those results of lookup data into black box simulators, like CarSim or VICar real-time, and implement an optimized vehicle model with those parameters. That in itself has its limitations, particularly if you want to make any changes to the either to the car chassis topology, or even just to generate new parameters. You have to go back to Adam's car to do to regenerate any new parameters and lookups to do that. So it's a somewhat cumbersome exercise, and certainly John's team has found it very valuable to be able to just do this within the MapleSim environment. So this got us asking the question, wouldn't it be great if you could easily transfer Adam's car model directly into MapleSim and integrate it with all of the vehicle systems, powertrain, and electric drives and so forth, and and be able to do this without tying up an Adams license. You've done the work in Adams, now you just want to use a certain representation from the Adams car environment for doing further work. And also the notion of being able to generate real-time capable code of your Adams car model for doing hard-on-the-loop, drive-in-the-loop, component-in-the-loop types of testing. So these are two really valuable, I think, major valuable propositions for going down this route. And we actually believe that, given some of the initial studies we've done, is that it would be relatively straightforward for us to develop a tool that would extract the system topology, all the suspension, steering, driver, tires, and the information from the Adams car environment, and then implement it to a certain degree of fidelity. It may not be everything that's in Adams car, but enough that can be implemented in an equivalent chassis model for then being able to add the further multi-domain subsystems to the full vehicle model. So this is the, if you like, is the product that we're proposing to in this meeting, and the question for us is to get an understanding of how valuable you would actually feel this would be as a tool. Actually, just to finish off the product storyboard, you can then use the MapleSim connector to generate codes that can then take the entire vehicle model or parts of the vehicle model, including the chassis topology, and bring that into the Simulink or other tools that are used for doing that require fast code for doing either in-the-loop testing or for doing optimizations or other in-house design tools, by using our code generation to do that. Just to give you a sense of what the real advantages are in terms of the code performance or the model performance. This is just a benchmark that, in fact, Andrew carried out for us, just to get a sense of what we're looking at in terms of the performance benefit. And you can see here that this is just using the one of the standard Adams car examples, the MDI demo vehicle, going through a double-lane change maneuver. That the Adams car model is significantly slower than the equivalent model in MapleSim, and this is critically important, particularly for real-time applications, where you very likely you would want to have a model that's going to be able to run within a 1 millisecond time budget. And clearly, the Adams car model will not be able to do that. Within MapleSim, we are well within that budget and can provide a significant amount of sort of computational headroom for you to add further detail to the vehicle model. So this is really one of the critically important results of being able to use a tool like as we are proposing. At the moment, you can do this manually, but what the idea is that we can provide a tool that will allow you to do this automatically.